Assalamu alaikum, everyone. I think in the last class, sorry, for May 25 batch, actually, I didn't do the last class, but I did uploaded the, recordings for all the files. If I just go back to your classroom for the May 25 batch, not for the Jan people, you guys can see that in your classroom, I have uploaded the fluid flow files and Hooke's law, momentum, work done. Over here, you guys already attended all the class up to Hooke's law. Only fluid flow, that was the only recording that you guys have to watch as a video before this question paper. I hope all of you guys finished watching this file for fluid flows, and this was it for unit 1. After this we will do some question paper, like chapter wise question papers, but I just want to start with one year wise question paper, since your school's mocks are starting, so that's why we're going to do some question paper today and also tomorrow. So in this file over here, this is your May 2019 Tuesday 14 unit 1 paper. Over here, in any cases for AS physics, for entire A levels physics, actually your question is always divided into two sections. Wait 1 minute, please. I think others are joining. Just 1 minute. Okay, now as I was saying that your AS physics papers, that means both AS and A2, the question papers are going to be divided into two sections, right? The first sections are MCQ. Section A contains 10 questions. 10 questions. This is your MCQ part, and from after that, your theoretical part question starts. Okay, this is your section B questions. Question 11 to mostly they extend it to like 18 or 19, not more than 19. In unit 2, you guys will see they might ask you questions up to like what, 22 also, but for questions in unit 1, they will mostly stick to just 18 questions and not more than that, right? Or maximum 18 to 19 questions, not more than that. So if we start with your section A today, the MCQs, this is about quantities and physical quantities and units which you remember. In quantities, physics are classified as either vectors and scalars, and which of the following units is only used for scalar quantity. I think we already did this as a worksheet questions on in our vectors concept, right? I can understand that this could be speed or velocity, so obviously this doesn't exactly say which one is it. I have to specifically say this is the quantity for a scalar quantity. This would be density, right? Density is a scalar quantity. Other than that, we have force, which is a vector. We have acceleration, which is also a vector. So the only correct answer here is your density, right? Density is the only um, scalar quantity which has this unit. Now, after this, once in orbit around above the Earth's atmosphere, the engines on a rocket space are switched off. Which row of the table correctly states the resulting motion of the rocket and the law explaining this motion? Okay, when the rocket is switched off, which row of the table correctly shows the resulting motion of the rocket? Yeah, I mean over here they're saying that what will happen to the rocket when the 1 minute, the motion of the rocket and explanation. Once in orbit above the Earth. Okay, problem is that over here, even if you switch off your rocket, that means certainly I can understand that the thrust is zero now at this point, right? If thrust is zero, there was no other force acting on the rocket. This was actually acting as the resultant force. If thrust is zero, then we can also say resultant force is zero. In that reference, the acceleration was supposed to be zero. But in this entire example, we're talking about the orbit around the Earth, right? Orbit around the Earth means what? The orbit, or orbit above the Earth's atmosphere means this is a circular case, right? In circular plane or circular path, the direction always changes. Circular path, direction changes. So if your direction is changing, obviously at this point I can understand that magnitude wise there's no change in velocity, right? If your acceleration is constant, magnitude wise your change in velocity is zero, but direction wise there is a change in velocity. And if there is a change in velocity, obviously in that reference I have to consider that there is an acceleration. If there's an acceleration, there is a resultant force according to Newton's second law. So this is your option C. Option C is going to be the correct answer over here. Just because of direction, your velocity got affected. Since velocity is a vector quantity, since you have a change in velocity now, change in velocity creates a change in acceleration, or creates acceleration in general. And with whatever rate of acceleration, doesn't matter if it's a constant increasing or decreasing rate of acceleration, as long as the object is accelerating, doesn't matter at whatever rate, the object will always have a force acting on it. Is there any problem so far?
No, miss.
No, miss.
Okay, if there is no problem, then if we move on to your next part, this is about, I think, that fluid flow over here, the upthrust and drowning concept. Over here is that, sorry, 1 minute. Yeah, okay. As I was saying, the sphere of weight 2.5 Newton floats in water with half of its volume beneath the surface. Over here, this is your figure 1. In figure 1, you can see that this is the weight of this ball is 2.5, and half of the ball is under the water and the other half is above the water. And a force F is applied to the sphere completely immersing it in the water as shown. Which of the following is the minimum value of F that you have to provide to this ball over here or sphere over here in order to make it completely submerged inside the water? So this is your figure 2. Now, which of the following is the minimum value of force? I can only understand that at this point you have your weight acting and you have your upthrust acting, right? This is a steel condition. Steel condition means that over here there is no velocity, there is no acceleration. At this point, weight is equals to upthrust. If weight is equals to upthrust and weight was also given as 2.5 Newton, I can understand the upthrust that is acting over here is 2.5. Right. The reason that this sphere was completely balanced at this position because the weight of 2.5 Newton was completely balanced with the upward force of upthrust with the same magnitude. That's why the resultant force was zero and the object was at this point at a still position with no motion or no traveling. Now, if I want to submerge it inside, then I have to increase the downward forces, right? Downward forces means that obviously at this point also weight is there. And at this point, in this situation also upthrust is there. If I want to provide a resultant force, in this case, the resultant forces are going to be weight plus force minus upthrust. Sorry, minus upthrust. And in this case, I have to just overcome this upthrust, right? As you can understand, that the extra force that I'm providing doesn't oppose the motion of your weight, but the extra force that I'm providing onto this sphere opposes the motion of your upthrust. So that means I have to just eliminate this upthrust over here. I have to eliminate this upthrust in this example. So if I can eliminate this upthrust, I'll be able to entirely submerge it inside the inside this water body, inside the water medium. So in this case, in order to eliminate this, this is the case. Resultant force should only be your weight. If the resultant force is only weight, then you have to use the equation W plus F minus U. Then you have 2.5 plus, then force is also 2.5, upthrust is also 2.5. They cancel each other out, leaving you with only 2.5 Newton, which causes the ball to entirely submerge inside the water body now. So the minimum force you need to provide is the force force equal to upthrust. Obviously, on a maximum level, you can increase the force more than that, but the minimum force you need to provide onto this sphere in order to make it submerged entirely inside the water body is equals to the upthrust value, 2.5. So in that case, you have 1 multiplied with 2.5, right? That is the only answer here. Is there any problem understanding this question?
Yes, could you
No,
repeat
ma'am.
the last part again?
Uh, which part? Sorry.
Why you made F equal 2.5?
F equals to 2.5. In this example, the only upward force that is causing this object to float on the water body is this upthrust, right? And I
Yes,
don't
miss.
want it to float. So if I don't want it to float, I have to eliminate the upward floating force. So if I want to eliminate this upward floating force, I have to provide the downward force equal to that magnitude. This was a 2.5 Newton force causing the sphere to float on the surface. To eliminate it, I'll have to provide a 2.5 Newton force in the downward direction. Is this clear?
Yes, miss. Okay.
Okay, then anyone else have any questions from question 3?
No, miss.
No, ma'am.
No, teacher.
Okay, then if you move, this was again, I think you're in your equations of motion concept, but this is actually not an equations of motion, right? This is a projectile motion now we can see. Because over here you can travel like what? Vertical distance and horizontal distance. It was already stated that a ball rolls off a table with horizontal velocity 12, sorry, 1, 2. 1.2. This is, I think, a scenario 2 from your scenarios out of the 4 scenarios of a projectile motion. Initial velocity is given as 1.2. The ball takes 0.9 seconds to reach the ground and lands a distance s meters from the table as shown. Which of the following expressions could be used to determine the value of your s? You have to understand that s is a horizontal distance, right? We do not have the value for your time yet. We do not have the value for your time yet. Oh, sorry, the time was given. The ball takes 0.9 seconds to reach the ground and lands. The time was given. Over here, if the time is given, I can understand that for your horizontal component of the projectile motion, they always remain same, right? Doesn't matter wherever you go for your entire maths, it will always be 1.2 meters per second. And you can also not create any component because the initial velocity was entirely in the horizontal plane, right? It was not creating some component with the horizontal plane, it was entirely in the horizontal plane. So you just have velocity and time given, you just want to find out the speed, so you just want to find out the distance. Right, so you have to use the equation s equals to, it was actually u is equals to s over t, and from there if I make s the subject, it will be ut. For ut, we have 1.2 and 0.9. We don't need to multiply, but I can see option B is your correct answer here. Because obviously in horizontal motion, object moves with constant velocity. The only equation that we can use is v is equals to d by t. Any questions so far from this part? Okay.
No, miss.
Okay, then if we move on to your question 5 then. For question 5, it says that a sample of seawater is collected using a beaker and the sample contains some particles of sand which settle at the bottom of the beaker. Which of the following would result in decrease of the time taken for the sand to settle? The smaller particles of sand, 1 minute. A sample of seawater is collected using a beaker and a sample contains small particles of sand which settle down at the bottom of the beaker. Which of the following would result in a decrease in the time for the sand to settle? Smaller particles of sand, lower temperature, smaller terminal velocity, and lower viscosity of the water. Over here, I'm just saying that how much time it will actually take for the, smaller sand particles inside the water to eventually settle down at the bottom. So for that situation, the what was that? The sand particles actually need to move through the water, right? In order to settle down at the bottom of your water, obviously there will be some sand particles present at the very top surface of your water. These top surface sand particles need to move all the way down to the bottom of your beaker, right? So they need to travel through that. In order to travel through that, the smaller the particles of the sand, this doesn't have any effect with this. Smaller terminal velocity of the sand particles, smaller terminal velocity would indicate longer time. I mean, over here, smaller terminal velocity indicates that now the entire sand will take a longer time to travel to the travel to the bottom of your beaker. So this causes an increase in time. This doesn't decrease the time. And again, a smaller particles of sand means smaller particles of sand means that lower radius. I mean, obviously, some of you might not have watched the recording for the fluid flow at this point, but there is one formula that connects the terminal velocity with this radius calculation. That was, I think, v term is equals to 6 pi r eta. Wait 1 minute. It was actually f equals to 6 pi r eta v term. From there, if you make v term the subject, it will be f 6 pi r eta this value. Okay, and now they are saying that over here, the particles, little smaller particles of sand. Smaller particles of sand means radius is smaller, velocity is high. 1 minute. In that case, 6 pi r eta v term. 1 minute. F is equals to 6 pi r eta v term. Yeah, smaller particles would also not cause decrease of time for this sand to settle, because over here I'm not considering the sands to be a sphere. That is also one of the problems over here. In order to use this example, I have to consider this every sand particles are actually acting as a sphere. It was not stated, so we cannot use that that relationship over here. That radius and velocity are not related to each other. Now after this, if I want to, just 1 minute, please. Sorry, 1 minute. Sorry, as I was saying, now other than that, it also says that lower temperature of the seawater. Lower temperature doesn't actually directly affect anything about the flow of the sand particles inside any fluid, but lower viscosity of the seawater would result in a decrease in the time taken for the sand to settle. Yeah, lower viscosity means what? The entire liquid is now less thick, right? Over here, lower viscosity would indicate the entire liquid is less thick. Less thick indicates now, if you compare for an oil and water, right? Inside the water, you can easily move. Inside the oil, you cannot move easily because oil is more thick compared to water. That's why oil will have a higher viscosity compared to water. So any material with lower viscosity will have less resistance to flow. To like any material with lower viscosity means that any object that is going to flow through that material will receive less obstacles or will receive less resistance. With the smaller resistance, it can obviously achieve a larger speed and travel at a smaller time. Right? Smaller time means over here it would have a decrease in time. And again, also for yeah, it will actually have a decrease in time, right? This is the only case over here. Option D is the only answer that connects the time directly with the property of the liquid. Is this clear? Any questions so far?
No, teacher. No, miss.
No, miss.
Okay, then after this is about your what spring constant material stuff. Over here, they are asking that a graph of stress against strain up to the breaking point is drawn for 4 samples A, B, C, D. Which sample of wire has both a low elastic limit and a large region of plastic deformation? Low elastic limit means what? Over here, low elastic limit means that your graph's y-axis or your graph's extension and up to which the graph is linear over here. If I just draw this part, the straight line indicates that where the extension starts becoming, or where the graph stops following Hooke's law, or where exactly the graph starts to create a curve. So from there we can understand that where the elastic limit will stop. Low elastic limit is only this one, right? Option D has the low elastic limit. 1 minute. Low elastic limit and large plastic deformation. This is less steeper, more and more. I can see that C has a large plastic deformation, right? Because if you consider for D, at this point, you have your elastic limit, and after that, they have only deformed for a small region, right? If you now compare it for C, then this is your elastic limit, and after this, they are having a large plastic deformation. So between C and D, your answer should be A and B. Obviously, has a very high elastic limit, so A and B is out of your option. But C has a large plastic region, and D has a lower elastic limit. 1 minute. Which sample of wire has both a low elastic limit and a large plastic deformation? Yes, Aisha, you can ask.
Miss, wouldn't it be C?
Yes, it would be C actually. Yeah. On a naked eye, it sometimes looks like that, maybe D is higher, but exactly this is where, 1 minute. If I just use a much thinner line, I think we'll be able to watch that clearly. Over here for C, this is the elastic limit, right? Exactly after this, the graph starts to become create a curve. This is your elastic limit, somewhat below than this point also actually. Right, this is your roughly elastic limit, and for yours D, this is your elastic limit. Yeah, in that case, obviously D, C is the answer then, right? Somewhat below than this also, right? Yeah, this is the case. D, I mean, the elastic limit for C and D are very close to each other, but if you focus on the straight lines, then you'll be able to understand that no, D still has elastic limit few centimeters above than the elastic limit of C. So C would be your final answer. Right, so in order to ensure your elastic limit, you always draw straight lines, which is very starting from the origin and kind of acting as a tangent to the curve, so that you can identify that exactly from where the graph creates a curve. That is easier. That makes this process easier for you to identify the elastic limit over here. So maybe the somewhere over here, this was the elastic limit, and for it, this was the elastic limit. And in that case, option C is your correct answer. A large section of a nagging means that over here, the wire C was plastically deforming for a long time before breaking at this point. Is there any problem? So far, any questions from question 6?
No.
Okay, if there is no problem, then we'll move on to your question 7. It says that a water pump causes 200 gram of water to be ejected from the nozzle of a garden hose each second at a velocity of this. Which of the following expressions could be used to determine the minimum output power in watts required from the pump? This is your watt. And over here, the informations that they have provided you with, that this much energy and this much velocity, that means from there I can find out the kinetic energy, right? And kinetic energy, this is your output power actually, right? This much amount of water moves out of the pipe with a velocity of 3 meters per second, and it was also given as a time, right? Each second was your time. That means 1 second was your time, and they were asking you to find out the minimum output power. Power is energy divided by time, so we're just using the equation power kinetic energy divided by time, because we have been provided with the kinetic energy information. So I have to use kinetic energy. So you have half, then mass is in grams. So you have to convert that into kg. That's 0.2 kg. So you have 0.2 multiplied with 3 square divided by 1. If you simplify it, because I cannot see this in any of the answer, you have 0.2 multiplied with 3 square. This 2 from the half will go to the denominator and multiply with the 1 in the denominator. So you have 2 multiplied with 1, just 2. That makes your answer B the correct answer, right? 0.2 mass velocity square, and that half from the kinetic energy came down to the denominator and multiplied with the 1 in the denominator to give you 2. And this is it. Any questions from question 7?
No, teacher.
No, ma'am.
Okay, then this was actually one of the trickiest questions, I think. I think we already solved this a lot of the times in our maybe exams or worksheets. Over here, it says that the rocket, so a model rocket is launched and moves vertically upward while still burning fuel to give a constant upward thrust. The fuel runs out and the rocket reaches the maximum height at time t before falling back to the ground. Which of the following shows the acceleration of the rocket as it varies with time, and if the mass in decrease of the fuel burns is neglected? If I could that the engine was on. Okay, so this is the point for which your engine was on. If the engine was on up to this point, that means only force was acting on your rocket at this point was the thrust, right? So over here, resultant force was thrust. And because of that, obviously the particle will be accelerating. There's no doubt in that. Over here, because of thrust, the particle was accelerating. I don't know exactly at what rate, but it was accelerating. Now, after this, when the resultant force obviously decreases, but it also has some velocity here, right? Because if it was accelerating, then final velocity is obviously going to be have some magnitude. So there you have the final velocity greater than 0. Over here, you have the final velocity greater than 0 meters per second. Now, after this point, the engine turns off. If the engine turns off, then what happens exactly? When engine turns off, engine turns off means that now your resultant velocity, resultant force is 0 because there is no thrust, there is no engine to provide the thrust. If resultant force is 0, acceleration is 0, but it doesn't mean that all of a sudden your velocity will become 0. It means that now the initial velocity for this new section, independent of the engine, this new section of the journey is going to be equal to the final velocity of this point. Like whatever the final velocity with which the engine turned off, that is going to be the initial velocity for your new journey. And exactly at the maximum point, your object reaches the maximum height at time t seconds. Maybe it was said over here that the rocket reaches the maximum height at time capital T. So this is your capital T seconds. And exactly at this time, what happens? V is going to be 0, right? So all this time, your value for your acceleration was not actually 0. It was still under gravity. So I'll consider this time, your object was actually moving with 9.81 meters per second square, but in negative direction, right? Because it was actually decelerating. As you can see, the initial velocity for this section has some magnitude and the final velocity was 0. So obviously at this point, the object was decelerating with the rate of 9.81. After this, what would happen? After t seconds, at this journey, only weight acts downward, engine is still off. Over here, I never turned on the engine, so engine turns off and only weight acts. If only weight is acting in the downward direction, that means over here, your resultant force is equals to mg. And this time, you get the value of your A as g. If the value of your A is equals to g, then you get a negative 9.81 meters per second square again, because obviously downward direction, I mean, in your equations of motion, we always consider the downward to be negative and upward to be positive, right? And now again, if A is equals to negative 9.81, then what else do you have? A is negative 9.81, then you have V equals to, also, I mean, over here also the velocity was changing, right? So this is the main case. Your object was accelerating here, decelerating here, accelerating, but with negative direction. And again, exactly at time t, it didn't actually, shift to minus acceleration. Before time t, it would have shifted to, it has shifted to like, a negative acceleration. So this is your correct answer actually. This is the acceleration it was having, or it had in the situation when the engine was on. At this point exactly, the engine turned off. That's why for this section of the journey, Like, as you can see, for this section of the journey, the object was decelerating in the upward direction. So you have a negative 9.81, and after t seconds, the object will actually accelerate, but in the negative direction, so it will again remain at negative 9.81. So option C is your correct answer. Any question from this question 8?
No, teacher. No, teacher.
No.
Okay, if there is no problem, then we'll quickly move on to question 9. This is again a similar question we already did in the vectors worksheet classes, right? Over here, I have to create a vector diagram. I can understand the diagrams are diagram to scale. Okay, if the diagrams are to scale over here, so I just have to make the arrow for your 20 kilometer. I can understand after traveling 12 kilometer from this point, it will travel at a 340 degree for 20 kilometer. So if I just draw this, oh wait 1 minute, if I just copy this, okay. Now, I can clearly understand that this was the origin, right? And all my arrows are indicating to this point. So this is my final direction then. This is my final direction. If this is your final displacement, then I can understand that between point B and D, my final answer would be. But the problem is that your final displacement, like over here, I'm actually trying to find out the shortest distance from the origin to the final destination. Okay, I can obviously go to the destination directly over here. That would be my final displacement, or I could choose the paths followed by the student, that 12 kilometer and then again another 20 kilometer. This shortest line over here actually represents the displacement over here, and displacement means that is always going to be the shortest distance, right? So if this is the shortest distance and if this diagram is to scale, you have to consider that this one is actually is comparatively to 12 kilometer to 20 kilometer, this one is very big in size, right? That means obviously my final displacement cannot be greater than the individual distance length. My final displacement should always be the shortest distance. That's why option B is your correct answer. So over here, option B is your final correct answer. Is this clear? Any problem from question 9?
No.
No.
Then after this, if we move question 10, a lift moves upward from rest with acceleration A. A student of mass 70 kg standing in the lift exerts a force of 800 Newton on the floor of the lift. Okay. Which of the following expressions could be used to determine A? This is kind of like the M1 questions, right? Over here, a lift was moving upward from rest with acceleration A. A student of mass 70 kg was standing in the lift and exerts a force of 800 Newton on the floor of the lift. In the lift and exerts a force of 800 Newton on. Okay, then I think this is how the scenarios are going to be, right? There's a person on the lift. I'll just consider the person as a like what? As a overall block over here. It says also that in the lift exerts a force of this on the floor of the lift. Okay, you have to understand that obviously 70 G means that weight is acting 70 Newton G over here, right? This is the weight of the person or student on the floor of the lift, and also this 800 Newton. What is this? This is not weight. This is actually the pair of the reaction force. Over here it says that in standing in the lift exerts a force of 800 Newton on the floor of the lift. This 800 Newton is actually acting on the lift, right? But which of the following expressions could be used to determine the value for your A? Yeah, this is the force acting on the floor of the lift. That means if you want to identify that, one problem over here is that I can also find out the A in terms of the lift and in terms of your person also. The problem is that if you're considering about your maybe lift, then obviously there's a weight from the person acting in the downward direction, and because of the reaction forces pair, there is a 800 Newton acting in the downward direction also on the lift. Okay, so if you want to write the equation in terms of the lift, there will be a problem. You have 800 plus 70g plus mg. So plus ma. What is the value for your m? Do you know the mass of the lift? We do not know the mass of the lift. So that's where we get stuck if you want to work with the lift case. Now again, as I've already stated, that this 800 was what? 800 was actually your pair of the reaction force, right? According to Newton's third law pair, every action has equal and opposite reactions. So the just because of the ground is going to provide me a electrostatic reaction force in the upward direction, I will not stand there receiving the force only. I will also react to that electrostatic upward force by exerting the same electrostatic downward force onto the lift, right? So this 800 Newton was actually the electrostatic upward force, so electrostatic downward force from the person on the lift, but this is again acting on the lift, right? But if you're considering on the person, if you're trying to find out what are the forces acting on the person, then on the person you have only weight acting in the downward, earth is pulling the person downward, and from the lift, from the floor of the lift, the person is receiving a electrostatic reaction force in the upward direction of 800 Newton. So you have 800 upward, 700g downward, and obviously the person was still connected to the lift, right? So if the lift was accelerating at A, person would still be accelerating at A. This is what we call as relative motion. Over here, I'm connected to lift. That's why if lift is moving at A, I'll also be moving at A. So then you write down the equation in terms of the person, and you have 800 minus 70g equals to 70A. Now we can complete the equation because we knew the mass of the person. So which is option C, right? Option C is the correct answer. Right. Is there any problem from this part?
No, teacher.
No, ma'am.
Okay, if there is no problem, then we're going to move on to this. I think this was included in your forces worksheet. Over here, this is actually a part of your forces worksheet. It's not a star mark question, but still this is an explanation. It says a child standing on a skateboard, and both are stationary. The child throws a ball forward and high velocity at a high velocity, and the child and the skateboard moves backward at a lower velocity. Okay, over here the ball moves with a higher velocity, but the child and the skateboard combine to that, like they combined system, they move in the backward direction with a lower velocity. Explain in terms of momentum why the child and the skateboard move backwards at a lower velocity. Over here, this is actually about your momentum example. Your momentum, we actually follow the equation mass times velocity. Okay, now in this example, we'll follow the law of conservation of momentum. In cases of a law of conservation of momentum, what happens? Your sum of momentum before collision is actually equals to sum of momentum after collision. One thing to understand is that I'm going to consider the mass of the child and skateboard as mass 1 and mass of the ball as mass 2. So this is your mass 2 and this is your mass 1. I can clearly understand that mass 1 is huge compared to mass 2. Right? Mass 1 is the mass of a person, mass of a skateboard, which is obviously a large value compared to the mass of only small ball. And over here, if I consider that m1 multiplied with their velocity was 0, m2 multiplied with their velocity was also 0. But m1 had some velocity and m2 have some velocity in the But in this example, m1 v1 minus m2 v2, if I just rearrange them, we get m1 v1 equals to m2 v2. At the end over here, in this scenario, in order to follow the law of conservation of momentum, since your initial momentum was 0, your final momentum for the mass one, which is the combined for your person and skateboard, has to be equal to the total momentum of your ball. And again, over here, the mass of the ball was like very small compared to the mass of the mass of the skateboard and person, and smaller mass can always achieve a larger velocity, because according to the equation, momentum, if I just make mass the subject of the equation, it will be 1 over v multiplied with momentum. What you can understand from this is that mass and velocity are inversely proportional. If mass and velocity are inversely proportional, for the ball who have a smaller mass will have a larger velocity, and for the system of mass of person and the skateboard who have a larger mass will have a smaller velocity in order to balance each other out. Is this clear? Any problem from this explanation of question 11?
No, miss.
No, ma'am.
Okay, if there is no problem, then we'll quickly move on to your answers part. You're not supposed to write down the answer in terms of these equations, but we have to say that initial momentum of the ball, child, and skateboard was zero, since they didn't had any velocity, or since they were all stationary. And due to conservation of law of conservation of momentum, the total momentum before collision is must be equals to total momentum after collision. So the momentum of the child and skateboard must be equal to the momentum of the ball. Um, yeah, must be equal to the momentum of the ball. And what else? What the chance of move backwards? And also the lower velocities, because larger the mass, the object can only have a smaller velocity in order to balance out the magnitude. These are the 4 points over here. I cannot say collision over here because they're throwing the ball. So before throw should be equals to total momentum after throw So the momentum of your child with skateboard should be equal and opposite to the momentum of ball. So they cancel each other out, ensuring the zero momentum. And then again, the mass of the child skateboard is greater than the mass of the ball, and therefore the velocity will be smaller. You can refer to the equation that P is equals to mv. Right, from this, we can understand that objects with larger mass will have smaller velocity. Okay, so this is for question 11. Is there any problem from this explanation of question 11?
No, ma'am.
If there is no problem, then we'll quickly move on to your question 12. Now, over here, this
Sorry,
is, I think, about.
Miss, could you just stay there for like 1 minute? Just I'm almost done with it. Okay, thank you, Miss.
Okay, then if we move on to your question 12. Question 12 is, I think, about energies, right? Yeah, efficiency. The machine would make work easier by changing the size or direction of the force. A student designed a simple machine to lift a box of 50 kg. The student claimed that the efficiency of the machine was greater than 90%. Okay, 1 minute. And the machine used a slope of 2 meter. Length is 15 meter to move the box. 2 meter height, length is 15 meter. The force was connected to a the box was connected to a 8 kg mass by a rope over a pulley as shown, and 8 kg mass fell. The box moves up the slope at a steady speed. Okay, I can understand that over here, by the time that 8 kg mass will fall, obviously they're connected to each other, this 50 kg mass will also move 2 meters above the ground, right? Over here for the 50 kg, they will not travel the 15-meter distance. They will only travel the 2-meter distance because the 8 kg mass can only fall the 2 meter distance, right? So determine whether the maximum efficiency of the machine was greater than 90% or not. Because in this part, the student is claiming that in this process, the efficiency of the machine is greater than 90%. So in order to explain that, I can understand that even if I want to find out the, I can understand that gravitational potential energy is my energy input here, right? This is my energy input because first this mass needs to fall down and only then the 50 kg box will move up the slope. So this is your GPE and this is acting as my total energy input. If I'm talking about efficiency, then I'll obviously have to work with energy input and energy output. This GP is acting as my input, and what is my output here? Output is this one, right? The actual amount of work is done by the box to move the 2 meter distance. That is your output. But problem is this time the box was not a horizontal plane, it was on an inclined plane. So I have to find out the components over here. This is your 50G, and I need to find out this angle. 1 minute. I can find out this angle from basic trigonometry. Opposite is 2, and what is this? Hypotenuse is 15, so we have to use sine here, right? I can clearly see this creates a right angle triangle. This is 2, 15, theta 90 degree. So in order to find out theta, we have sine inverse 2 over 15. Yeah, uh, 2 over 15, right? Okay. In that case, we get the value for your sine, or maybe we can write this as what? Sine theta as 2 over 15, because I anyway just need to work with the sine theta component, not with the theta entirely. You'll see over here, this is your horizontal component 50 cos theta, and this is your um this is a vertical component. This is your horizontal component 50g sine theta. This is your reaction force, and in order to make the object move up the slope, I have to provide an upward force, right? This upward force must be equals to this one, right? Otherwise there's no work is done over here. In order to make this a box move up the slope, I need to do some work against this. So this force is actually equals to this one. Okay, I have to provide force enough to overcome this force. I'm doing work against this force. So my work done force for my work done calculation, the amount of force that I'm going to use is 50g sine theta. And what else that I'm using? Yeah, 50g sine theta actually over a 2 meter distance, right? Yes, Aisha, you can ask.
So Miss, F is 50G sine theta.
Yes. 50 g sine theta.
Wouldn't it be greater because it has to move upwards?
It can move upward at a constant velocity, right? Steady speed.
Okay, fine.
Then over here, I can find out my energy output also using the what? Over here, I have like force into distance I'm using, right? So you have the efficiency calculation. Yes, Arif, you can ask.
Teacher, so based on the diagram, this is my assumption based on the diagram, okay? So if the machine was if more than 90% efficient, okay, wouldn't the 50 kg mass be near the pulley instead of it being way further away?
Oh, problem is that it's saying that 50%, sorry, 90% efficient means that most of the gravitational potential energy, like the loss of gravitational potential energy, is getting converted to this work done, right? That's what it means. But it doesn't mean that it is going to be like, higher up the plane or closer to the pulley. How can it be closer to the pulley? Because they are connected to each other. This 8 kg mass can only fall 2 meter, right? Because the height over here is 2 meter. So this can only fall 2 meter downward. As they're connected, if 8 kg mass falls 2 meter downward, this box on a maximum can only travel 2 meters above the plane, not 15 meters. Right? Efficiency means that how much of what percentage of the input energy is getting converted to the output energy. It doesn't mean that how effectively I'm doing the work, right? How much closer this box is going to be up the plane or close to the pulley. This doesn't mean the efficiency. Efficiency means what percentage of the input energy is getting converted to the output energy. Is this clear? Okay, I think he left. Maybe he has some problem. So, anyone else have any problem?
No, teacher.
No, teacher.
Multiplied with 100%. Yeah, we have to do 100% here. So, output energy is what? FD, FD, 1 minute, Arif, just 1 minute. FD is actually 50G, 59.81 multiplied with sine theta. I already know it's 2 by 15, right? Multiplied with 2 and then dividing this with your mgh, which is 9.81, height is 2, and multiplying this with I think 100%, right? Can anyone please calculate this for me? Like what is the value that you get from here? We can simplify it. This and this cancels out, this and this cancels out. Now try to calculate it. And over here you just have 50.
That's 83%.
83%, then 83%. So obviously the student was wrong in that case, right? This is less than 90%. I'll explain that. But before that, Arif, how much did you listen to me last time?
I listened it for just like 10 seconds.
Okay. Okay, then I'll explain again. Efficiency over here, it doesn't mean that, how close the object is going to be closer to the, pulley or up the slope, right? It doesn't mean that I am doing this entire, business entirely over here. I cannot complete it because in this entire example, this 8 kg mass is connected to the 50 kg mass, right? There's no possibility that the box can move closer to the pulley because you can understand that slope length was 15 meter here, right? And if the 8 kg mass can only fall 2 meter downward, this box can only move above for 2 meters, right? It cannot travel a larger distance if this block is only moving 2 meters downward. As they're connected, if the block moves 2 meter downward, this box can only move 2 meters above the plane. And another thing, over here, efficiency indicates that what percentage of your input energy is getting converted to your output energy, right? Efficiency means that what percentage of your input energy will get converted to your output energy. It doesn't indicate that how much closer this 50 kg is going to be to the pulley or something. Arif, is this clear?
Yes, teacher, it's clear.
Okay, then finally I have to write down a statement here since the student's conclusion was wrong. So I have to say that efficiency is 83%, so less than 90%, right? So conclusion wrong. Okay, 1 minute. Assalamualaikum everyone. In the last class we completed up to question 12, so we're going to start with question 13. Question 13 is I think about your kinematics, right? A swimmer swims a 100-meter race. A simplified displacement time graph for the swimmer is shown. This is a simplified displacement time graph. We need to describe the corresponding velocity time graph for the motion of the swimmer on the axis below, and we have to show all the working in the space below. Like if you have to do some working, you have to show that again. I can clearly understand that this parts, right? That means up to your 42 distance or 42 time, and from 1 minute, yeah, up to 42, the graph was a straight line, and again from on the other side, up to 40, like from 48, the graph again starts to become a straight line. So only from 42 to 48, the graph was a curve. And for that curve, I can understand that that curve over here represents acceleration, right? But before that curve, after that curve, the straight slant line sections on the distance time graph or displacement time graph actually represents velocity, right? Constant velocity. So in that case, what will be the constant velocity? The distance traveled here is 48 meters over 42 seconds, right? For both the cases, the distance traveled was 48 meters, 48 meters. So we can understand that over here, 40 for your first distance, velocity will be 48 meters over 42 seconds, and that gives you 4842, which is 1.14 meters per second. And then again from there, from 52 to 90, right? From 48 to 90 actually. That is how much? 48 minus 90, that gives you another 42 seconds. That means over here also from 48 distance to 48 seconds traveling, after 42 seconds traveling, I'm going to get the same velocity, which is how much? Actually, it's 1.15, yeah, 1.15143. So this is the velocity that I'm going to get. So I have to write this down over here, that up to 42, 1.14, right? If I consider this is 0.515, this is going to be 1.14 is supposed to be somewhere over here. And then similarly on this place also, it should be from 48 to 90. Right? And then last, connect the both the curves over here. Right? I just have to connect both these curves using a straight line. In both these parts of the graph using a straight line. Right, so this is how the graph is supposed to look. I think we did this in some kind of our worksheets, right? This was maybe 1.14 positive, and this is your 1.14 negative velocities. They have, yeah, this is it actually. Other than this, nothing else have to be written on the graph. And this was all the working we need to do. Now, after this, they are saying that to increase the initial speed, the swimmer begin the race by gliding underwater for 15 meter and then begin to use her arms and legs. This was not represented on the simplified displacement time graph. We need to sketch on the axis below to show the actual variation of the displacement with the time for the first 15 meter of the race. Okay, what exactly happens over here is that in order to increase her initial speed, the diver will not just start moving in a straight line. The diver will just first dive inside the water body for 15 minutes or for 15 meters and then starts moving up. Okay, so for this section, we have to draw the displacement time. In this case, what happens? Over here, as you go inside the water or as you go more deeper in the water, then your velocity will be decreasing, right? Because your water pressure increasing or your resistive forces from the water. As I was explaining. So, as you dive more into the water, your velocity actually decreases. So if your velocity is decreasing, that means this is how the graph is supposed to look. 1 minute. This is your 15-meter level with 14 seconds at the when over here they're saying that when and this diver was traveling this 15-meter inside the water within this 14 seconds. So now over here, if I have to draw the graph is not going to be a straight line because this 15-meter would not be traveled with a constant velocity. This should be more accurate. So for more accuracy, the velocity is actually decreasing. The more you dive into the graph, dive into the water, the higher the depth, the smaller the velocity. So for that, the graph is going to be like this. Like, initially it's going to have a much more higher gradient, and finally it's going to have a lower gradient. Indicating gradient over here obviously represents your velocity. Is this clear?
Yes, teacher. Yes, miss.
Okay, then for the last part, if I explain one other way in which the motion of the swimmer has been simplified when drawing the displacement time graph. The other way for the simplification over here was that in this case, I consider the velocity to be constant for that, before and after 42 seconds and 48 seconds, which is not probable, which is not possible, right? If velocity is constant, that means I am assuming that for each stroke, the swimmer was traveling same distance, and for the same amount of time, the swimmer was actually applying for each stroke, which is impossible because how many distance I'm going to travel after each stroke or during each stroke, that is not a fixed variable, right? I cannot keep it constant. So if that is not constant, then maintaining the constant velocity is also not possible. So this is one case that the constant velocity on the graph represents that the velocity is constant during each stroke, which is impossible for the swimmer to maintain, right? So that was one of the simplified part of the displacement time. Yes, Aisha, you can ask.
Miss, in the graph, you gave negative 1.14 for both in the positive and negative axis. Is that correct?
Yes, yes, and positive and negative axis.
Why is it negative 1.14 in the positive axis over there?
Oh, because over here this is your downward sloping, right? In this case,
No,
what
miss.
happens?
I mean, when you drew the velocity time graph.
Yes, I took the velocity time graphs information from the displacement time graph, right?
I mean, miss, you wrote negative 1.14 for both of the values.
Oh, sorry, right, sorry. This is supposed to be positive. Sorry. This is positive, this is negative.
Okay, miss.
And if we write over here, the graph shows constant velocity. What is it? I was saying, sorry, 1 minute. The graph shows constant velocity which was constant, right? This is about obviously simplified idea. This is not possible. Then this is it for your question 13. After this, we're going to move on to your question 14. I hope there's no problem from question 13.
Miss, I didn't understand the question actually because I just joined a few minutes ago.
In that case, you'll have to watch the recording. Okay.
Okay.
Then I hope there's no other problem. We'll move on to this one. Over here, they're saying that the firework is designed to explode at a maximum height of 350. State that the vertical component of the velocity at launch is what 80 meters per second. Okay, vertical component means what? They're saying that the maximum height is 350. That means they're assuming this part of the equation of motion scenario. From the ground, on a maximum height, they will travel 350 meters above the ground, right? So this is your 350 meters above the ground. Initial velocity, they're asking you to calculate it. So u is what you have to calculate, but final velocity, the maximum height is always zero. And in the upward direction, always the vector quantities are positive, but over here the object is decelerating. So a is negative. That means over here u becomes v square minus 2as everything under root, where v is entirely zero. So you have minus 2 minus 9.81 and then 350 multiplied with the square root. After this calculation, I'm going to get 82.9 meters per second, right? So this is the value for your initial velocity. Is this clear? Any problems so far from this A part 1? So
Miss,
then
why
after,
is acceleration negative?
because object is decelerating, right? Over here, your initial velocity was something and the final velocity is zero. So decreasing velocity only indicates your acceleration is decreasing, right? So your acceleration is negative.
Um, isn't isn't A is equals to 9.81 in the case of vertical acceleration? There are like two motions. It's like a projectile motion, right?
In this case, I was only focusing on vertical components. So I'm not actually considering this thing as a projectile motion.
Oh, okay. I'm sorry. I didn't notice that part.
Okay, then if I move on to this next part, the vertical component of the velocity at launch depends on both initial velocity of the firework and theta. Okay, the vertical component of the velocity at launch, like the uv, that depends on both the initial velocity u and also the value of theta, the angle between the initial velocity and the horizontal. We need to sketch a graph showing how the initial velocity required for the firework to reach the maximum height of 350 varies with your theta for the firework. You have to understand that uv is actually u sine theta, right? For your sine theta, what exactly happens? I mean, obviously, for your initial velocity, if your initial velocity is increasing 1 minute, sine theta, sine 30 is half, sine 60 is 0.87, right? If theta increases, then the value for sine component actually increases, okay? But this is how you can actually write down the changes. For UV, both U and sine theta create some change, right? I mean, over here, not exactly, yeah, sine theta actually over here creates the change. So in this case, if you are using if you are changing the value for U only, in that case, what will happen? If you're changing the value for U, for example, if you have your U equals to 5, U equals to 6, and equals to 7, then UV becomes 5. I'm just using sine 30 degree, okay, keeping the sine theta constant to make sure that what effect does this change in U causes to the vertical component of to the velocity. So sine 30. So you get 5 sine 30, which is actually half. So you have 2.5, then 3, then how much? 3.5, right? What I can understand is that increasing the initial velocity increases the value for u. And again, increasing the value for your theta increases the value for your sine theta. Yes. I mean, again, if I draw a graph for uv with sine theta, over here, if I increase the value for theta as 30, 60, and 90, then you will see that over here I'm using 5 sine 30, 5 sine 60, and 5 sine 90. So this is 2.5, this is 1, and 5 sine, sorry, 1 minute. 5 sine 60 is actually 4.33. Sorry, man, that is 5 sine 90 is how much? 5. Right, this is 5. What I can see over here, that both the vertical component of initial velocity is directly proportional to initial velocity and sine theta, or just theta, right? So you have to understand that, okay, if the equation is u v equals to u sine theta, then if you make u the subject, it will be u v multiplied with 1 by sine theta, which means that u and sine theta are inversely proportional, right? If the maximum value of your, so if u increases, then sine theta must decrease, or if sine theta decreases or sine theta increases, u must decrease in order to keep this constant. Right? Is this clear? Sine theta or just theta you can write. Is this clear? Any problems so far from this part? The relationship between theta and initial velocity.
No, miss.
No, miss.
No, teacher.
It's not clear, or is there any problem?
It's clear.
Okay. Now, if this is the case, then I will, okay, if this is the case, then I'll just remove this. This is not needed. One thing I can understand that obviously then we get the maximum, over here the graph is going to be in decreasing, exponentially decreasing shape, right? And one thing to understand that at sine 90 is 1, right? And at sine 90, if sine 90 is 1, then at this point, the little minimum value that I'm supposed to get in order to reach that 350 height, because over here also, I have to make sure that I still reach that maximum 350 height. So for the 350 height, the minimum velocity was how much? 82.9. So this 82.9 can only be received if you're going to use the minimum velocity, but sine theta is 90 degrees. So this has to be mentioned, ensured here. So this is your graph. Is there any problem so far from this particular question?
No, miss.
No, miss.
If there is no problem, then over here it kind of looks like we have to use projectile motion, but we don't actually have to use that. We just have to use basic trigonometry here. A student wanted to estimate the maximum diameter of the firework after exploding, and the student estimated the time taken between seeing the firework explode and hearing the firework explode. And phi is the top of phi is the angle phi from the top of the bottom of the firework, from the top to the bottom of the firework. Okay. Describe how the student could measure the diameter of the maximum, should determine the diameter of so determine the maximum diameter of the exploded firework using the estimated data. Over here, I'm just going to consider this is a straight line. Then this is your diameter. And then this is another straight line, right? This angle is half of that phi. This is half of that phi. And one thing again, I can understand that this is going to be 90 degree, right? Because this kind of creates a triangle, and this side is actually acting like a, what is a tangent, right? So radius and tangent is obviously your 90 degree. If that is the case, then this is your radius and distance from the, but that is not also given, right? time taken between the firework, the angle this is given. Yeah, I have to consider that as the distance, right? Distance from the point the firework is released to the point where the firework would actually, emit or will explode. So we have this as radius, opposite over adjacent. So which is just what? Opposite over adjacent is tan. So we can get tan pi by 2 is equals to radius divided by b. In that case, we have the value for radius as d tan pi by 2. And again, this is for your radius. For your diameter, we have to use d is equals to 2r. In that case, d becomes 2d tan phi by 2. Right, so this is your expression that you can use roughly to determine the diameter of the firework after it exploded far away from the point of release. Right. And again, how can you find out this distance? Because in this case, they have already calculated the time taken between seeing the firework explode and hearing the firework explode. That is your time taken. So time can be calculated. Speed of sound over here, that was again measured from this part. The perpendicular distance was actually calculated in this way. Distance perpendicular was actually time multiplied with speed of sound. No need to introduce that into the final equation. You can just write d 2d tan phi by 2. That is enough. But this is how we'll also measure the value for distance. Otherwise, how would I measure that how far from my point of release the entire firework exploded, right? For that distance calculation also, I have to use the speed of sound and the time taken for that firework explode. Is this clear? Any questions from this question 14?
Clear.
No
If
question.
this is clear, okay, then we're going to move on to question 15. I think this is about some estimated question, right? Where you have to, yes, estimate the total length. Okay, now in this case, they're saying that muscle moves body parts by contracting and relaxing. And for the forearm to hold a ball in the position shown, the biceps muscle contracts, creating a tension in the muscle as shown. Okay. The student modeled the forces on the forearm using a uniform beam by spring arrangement. I mean, this is the assumption of the student for the arrangement of the muscles in the forearm. As shown below, the length and weight of the beam were the same as the length and weight of the forearm. Okay. Diagram not to scale, and these are the dimensions given. And now they are saying that it can be assumed that the bicep muscles act as a spring at an angle of 70 degrees, 4 centimeter from the pivot O, and to determine the tension, you will need to estimate the total length of the forearm, force of the ball on the beam, and weight of the beam are given. So one thing I have to identify, the total length of the beam is not given. I have to estimate that. For that estimation process, I can understand that if they're considering this much length as 4 centimeter, right? And this much length as 9 centimeter. So how many of these 4 centimeters and 9 centimeters can actually fit in there? I can understand they can fit in 2 9 centimeters. This is 18 centimeters. Copy. Then again 4. Right. And how many? Let's see. 4 and I think roughly we'll be able to fit in. Yeah, in that case, 4, 5.2 or something amount of 9 centimeters we can fit in. So 9 multiplied with 5.2, if you multiply, you get 46.8 meter. Okay, so this is how roughly I'll estimated the total length. Using this type of calculations, I can say that okay, not exactly also 5.2. This is like what 5.1. So 9 multiplied with 5.1 gives you 45.9 centimeters. So I'm going to assume that over here, the total length of the beam is 45.9 centimeters. You can also keep your assumptions into any values in between this. Okay. They're obviously going to give you a range of values that will be accepted over here since they're asking you for estimate this. So we have 45.6 centimeters or sorry 45.9 centimeters. Okay. Now after this we want to find out the value for your tension. So the value for your tension was inclined. Means I'm going to focus with the vertical component of the force, right? Because all the forces are in the vertical plane. So we have your tension sine 70, 70 degree. And also I'm considering that weight is acting directly at the center. Okay, weight of the beam was given as 15 Newton. That is this much distance is I'm considering its total length was 45.9. Let's say that this is roughly 46. Okay. So if you're taking 46 divided by 2, then it will be 23 centimeters from the pivot O. And the ball is going to be how much? 46 minus 9. That is 37 centimeters. Right. And these are the distributions of distances that we need to know. And now I can clearly understand that if you take this as a pivot, both the weight of the beam and weight of the ball make the beam move in the, what is this, clockwise direction. And only tension makes the beam move in the anti-clockwise direction. So we have to write the total momentum, total moment anti-clockwise equals to total moment clockwise. And in that case, what do we have? We have your tension sine 70 degree multiplied with whatever the distance was, 0.04. And then again on the other case, you have your 4.5 with 0.37, adding this with 15, I think. It's 15, then 0.23, right? So from there, you get the tension as 4.5, 0.04, adding this with your, so 0.37. Four point five, 0.37 plus 15, 0.23 divided by 0.04 with sine 70. And from there, you get 136 Newton roughly as the value for your tension. Yes, in that case, this is the working that you're supposed to do for your part B. So for your part A. Is there any problem from this calculation?
No, miss.
Now, this is the case, then we're going to move on to the next one. Explain one limitation of using a beam to model the forearm. Over here, the beam was, actually in real life, forearm is not symmetrical, but the beam was symmetrical, right? That is one problem. And since the beam was symmetrical, the center of gravity for the beam is going to be exactly at the center. But for the forearm, the center of gravity might not be in the middle, right? So these are the limitations of assuming this beam as a design for the forearm. The limitations are that the forearm is not symmetrical and center of gravity is not at the middle. The forearm center of gravity is not in the middle. And after this, I hope there's no problem from this question 15, right? And yes, Aisha, you can ask.
Miss, I'm sorry, but could you explain part A again?
Part A. For part A, I was just using your basics of your moment calculation. That I'm sorry, anti-clockwise moment and after that was the clockwise moment. If you're taking the moment from point O, as it was already given the question that you're supposed to take the moment from point O Then your weight and this weight of the ball, they're both moving in the clockwise direction, and this is moving in the anti-clockwise direction. So you have your force T sine 70 with four distance, and then your this is a 15 Newton, 15 Newton force and 4.5 Newton force. So this 15 Newton, 23 centimeters away, 4.5 Newton, 37 centimeters away. So I just rearrange the equation and make the subject here.
Okay, Miss.
Like,
Thank you.
the calculation was very easy. The only problem here was to estimate the length of the beam, which I assumed by measuring the 9 centimeters, like how many 9 centimeters are going to fit in inside the diagram, right? That was just an assumption. Okay. Now, if we move on to your question 16. Over here, this is about your, I think, materials part. It says that the student carried out an experiment to determine the Young modulus of copper. She used the apparatus below to observe the position of the marker as a copper wire extended under increasing applied force. Determine how the diameter of the wire would be determined. Over here, if you cut open a wire, this is how the wire looks like, right? It has a circular cross-section area like this. If you want to find out the diameter of this wire, that means this is a very small dimension that you are measuring, right? So for small dimension, you have to make sure that you are using a measuring instrument with higher resolution. Higher resolution means that if you compare with, for this kind of lengths, I can use meter ruler, I can use vernier caliper, I can use micrometer screw gauge. If I want to find out their resolutions, does anyone have any idea what is resolution? For your micrometer screw gauge, you have to understand, sorry, as I was saying, resolution means the smallest length that you can measure. Okay, so this has 1 millimeter, the smallest length that you can measure using meter ruler, then 0.1 millimeter that you can measure using vernier caliper, and then again 0.01 millimeter using micrometer screw gauge. So for this one, for 0.01 millimeter, for this one, you have to understand that as I'm using a very small data, or as I'm working with a very small dimension, in order to calculate this more accurately, we have to use the smallest resolution possible, or the smallest resolution that any device that is able to calculate. So we have to use the 0.01 millimeter, right? That means we have to use the micrometer screw gauge to find out the diameter of the cross-section area of the wire. And again, I cannot just, like take one measurement and take that as my final measurement. I have to take multiple measurements and then calculate a repeat to get a fair test, to get a accurate value. So what I can say is that I can use a micrometer screw gauge, and then obviously we have to take the reading from different orientation. That means from different angle, I have to take multiple readings and then calculate the average value. So that's why they're giving you 3 marks. This is a unit 3 pattern question, right? Because in our unit 1 classes, we haven't explained anything about these resolutions and all, right? This is a unit 3 pattern question. Now, as I was explaining that over here, there's, as I'm going to say that um, using a micrometer screw gauge, calculate mean. Now, after this, they have stated the student calculated the extension of the copper wire for each applied load. She then plotted the graph of load against extension. Yes, Aisha, you can ask.
Sorry, Miss, could you just show the resolution bit again that you wrote? Miss, is the veneer capilla nanometer or is it micrometers?
The micrometer. Millimeter, not
Oh,
micrometer.
sorry,
This is millimeter.
millimeters. Sorry. Okay, thank
Everything
you.
is millimeter. Okay, then after this, we are going to move forward. This is a force extension graph that we can see, and now they're asking you to determine the value for Young modulus of the copper from this. The original length and the diameter has been provided. I can understand that for, I mean, from the, what was that? From the derivations, Young modulus is actually stress over strain. Stress is force over area divided by extension over length. If I rearrange it, it's going to be force, length, area, extension, right? So over here, how much was the force? I have to use the direct, linear section of the graph. By the way, I cannot use non-linear section of the graph because for what was that? Your stress can only be calculated from the linear section, gradient, linear gradient from the stress strain graph also. So from the linear section of the graph, I'll try to pick out any easy coordinate from here actually. So easy coordinate means let's take this one. This is exactly what 3.4. 3.4 Newton, right? With 3.4 Newton, and extension was 1.5 and 10 to the power of minus 3 meter. This is the information that I'm taking, 1.5, 3.4, right? Okay. Now 3.4 extension, 1.5, so 3.4 Newton and 1.5 extension. Length is already given. The force was 3.4. Length is 2.4. And divided by area is pi r square, right? So pi diameter was given 2.3, we have to use half of that. So we basically have to use 2.3, 10 power minus 4 divided by 2, everything under square, and then multiplying this with extension 1.3, 10 power minus 3. Right, so using this derivation, we can easily find out the what was that Young modulus even from the force extension graph. 3.4 multiplied with 2.4 divided by pi multiplied with 2.3 10 to the power of minus 4 divided by 2 square into 1.5 10 to the power of minus 3, and that gives you the final answer as 1.3 into 10 to the power of 11 pascals. So we have 1.3 10 power 11 pascals, right? I can clearly understand all the values were given as one decimal place, so I also chose to keep my answer as one decimal place. And finally explain why the sample of wire used in this. Is there any problem from this part?
No, Miss.
No.
If there is no problem, then this is your star mark question, right? I hope all of you remember from the regular classes. Also, we have stated very frequently that in the star mark questions, your writing pattern will be judged. And again, you cannot just write all the points in a mixed up manner. You have to write all the points in a regular arrangement. Like I have to write about point one, then point two. I cannot mix up the arrangements over here. They're using that they're saying to explain why the sample of wire used in this experiment should be long and thin. First thing to understand that long and thin has something to do with the Young modulus. Longer the wire, sorry, uh, okay, long and thin, right? Thin means smaller radius, and longer wire means I can say that extension is when strain is extension over length. So if I write extension is equals to strain multiplied with length, where strain is now a constant. In that case, extension and length are directly proportional, right? So for longer wire, I'm supposed to get a longer extension, right? Another thing, why exactly longer extension is important for me because I'm going to conduct this experiment in a school. A school will not provide me with a large value of forces, to be honest, right? A school will on maximum provide me with 5 gram forces, 10 gram forces. These are very small forces in order to extend stiffer materials. If I want to extend, and again, for the smaller extensions, if I'm going to use a stiffer material, for this small amount of forces that are available in the school labs, they'll only extend for a small amount, right? For this small extensions, if I have to measure them, doesn't matter whatever the measuring instrument that you're using, vernier caliper, meter ruler, or micrometer screw gauge, you have to understand that the smaller the data that you're measuring, smaller data always give you larger percentage uncertainty. Okay. So now over here, if you want to make your entire experiment more accurate, then you have to use the idea that I have to somehow get larger extension. So for the larger extension, I'm going to use this idea that in order to receive larger extension, because to be honest, the length is not a problem for me. The length of the wire that I can use is any it is not anything matter for me. I can easily calculate that length or measure that length. But the length is actually directly proportional to your extension. If I'm going to use a larger length of a piece of a wire, for the larger length, I'm going to get a larger extension. And larger extension means a larger data that I'm calculating. A larger data means a smaller uncertainty in your extension calculation. Right? So far, is there any problem?
No, miss.
No, teacher.
And now we think about your, okay, then if you think about your radius. For the radius now, environment smaller radius actually indicates, mm, yeah, over here. Smaller radius actually indicates what? Stress, right? Yeah, 1 minute. It was stress, force over pi by 4 r square, right? Which I can simplify it as 4f pi r square, where 4 and pi are actually a constant because 4 is a number, pi is also a number. In this case, what I can say is that r square sigma equals to 4. 4 and pi is just a constant. So you can write, okay, this is equals to force. If this is equals to force, then in this case, radius is also directly proportional to force, right? If radius is directly proportional to force, 1 minute. If radius increases, in that case, the force is supposed to increase. Yeah, in that case, if I'm using a smaller radius means what? A smaller force will be able to extend the wire or something. No, 1 minute. No, this is not actually related to stress. I mean, for stress, if you connect it, I don't get anywhere. But if you connect this with the Young modulus, then we get somewhere. FLA extension, right? Radius was here. So now you consider radius is inversely proportional to your Young modulus. So if you're going to use a smaller wire will have a smaller radius will have a larger Young modulus, right? For a larger Young modulus, then again it doesn't, 1 minute. No, actually over here, if I just, from here also, if I make r squared the subject, I'm assuming that r squared is actually the area I'm referring to. Okay. So we have f p delta x. From there, what I can see is that radius or thin wire is inversely related to your extension also. Remember that my main motive over here, the main source of my percentage uncertainty was my extension, right? So if I'm going to use a smaller radius, that means a larger extension will be provided. If I'm going to use a thin wire provides a smaller radius. For a smaller radius is inversely proportional to your extension. This also increases your extension, right? And eventually, for all these cases, longer wire, thin wire, both of them favor my extension. And now I will be getting a larger a larger value of extension that I have to measure. If I'm using the larger data, then obviously the percentage uncertainty is small, and I'm going to get a much more accurate data from here. Is this clear?
Yes, miss.
Yes, ma'am.
Yes, yeah, it's clear.
Yes, ma'am.
And another thing, since force is directly proportional to radius, that means obviously in this case, I can use a smaller force on this long thin wire to get a larger extension, right? All these things have to be kept in mind when we're going to arrive at this answer. The first thing we're going to write is that the longer wire provides a longer extension. Longer extension is delta x, 1 minute, delta x is equals to measuring larger extension makes percentage uncertainty smaller. So data become more accurate, right? So this is your case actually. After this, you can also write that also for a smaller also for a smaller force, now can be used on this long thin wire to create a larger extension, right? Or larger extension. Okay, and the last questions are the last two questions, 17 and 18. I'm not actually going to solve that in the class today. I'll upload, I'll
The diagram shows a climber on a rock. A rope is kept firmly attached by a person on the ground and passes over a smooth loop to the climber. Okay, the climber slips and falls a distance as shown. Smooth loop. Okay, there's a person at the base of this rock, and there's a climber climbing up the rock, and between them there's a rope that is again passed through this one loop over here. So when this climber falls a distance, this loop will be still connected to the first person. Okay, and due to some accident, the climber over here has fallen a small distance, and it says the fall factor is used by climbers to estimate the severity of a climbing fall is given by how severity for that fall will be. Total fall, height fallen before the rope begins to stretch, and total unstretched length of rope. Okay, it says that the climber slips and falls with a fall factor of 0.8. before coming to rest, and the energy from the fall absorbed by the climbing rope um, from the fall is absorbed by the climbing rope. Okay, and the maximum strain in the rope is 90%. Show that the maximum force acting on the climber due to the rope is about 10 kilonewton. We need to assume that the extension of the rope is proportional to its tension and total unstretched length and the mass of the climber. Okay. First, let's find out the height fallen over here. Total unstretched length is 15, right? And it was given that the fall factor over here was 0.8. So using this equation, we can calculate the total height fallen before the rope begins to stretch, right? So using that equation, we are calculating the height fallen before rope begins to stretch. That is going to be 15 multiplied with 0.8, which is approximately 12 meter. Okay, that means over here the climber has fallen 12-meter distance, and then again we can find out the extension. The extension was the maximum strain of the rope was 9%, obviously, of its original length, right? So extension is going to be 9%, which is 9 by 100 multiplied with original length was 15. So this is 1.35 meter. Okay, we need to find out the maximum force acting on the climber due to the rope is about, like, with what force the rope was actually holding on to the person. We need to find out that. Okay, now then again, if the person is falling a height, that means there must be some gravitational distance, like difference, right? From the fall and again from the extension, there will be two gravitational forces active, gravitational potential energy, decrease in gravitational potential energy for two cases. The height the person has fallen, and after falling that 12-meter height, the rope will also extend 1.3 meter, right? And because of that also there will be a small change in gravitational potential energy. So let's find out E grav from fall. That is going to be what? Mass into gravitational potential energy into height fallen. That was 71, 9.81 multiplied with 12, and you are going to get 8358 joules. Similar kind of working for E graph due to extension. That is again going to be what? Same mass, same 0.9, so 9.81, and this time the distance would be, height would be 1.35, which is 940.3 joules. Okay, now I know one thing over here is that whatever the gravitational potential was, that will be entirely converted to your work done, right? This is entirely equals to your work done over here. Wait. Mm, no, not exactly work done. This will be entirely equal to your elastic stored energy, right? Now how can you find out elastic stored energy? That was always half into force into distance, right? From the linear section of force against extension, we'd always get that elastic stored energy. So over here, change in gravitational potential energy is actually equals to your elastic potential energy, EL. And elastic potential energy, like change in gravitational potential energy, is going to be the summation of the two forces you got, 8358 plus 940.3. This will be equals to half into force into extension. So from this part, you can just calculate the maximum force applied on the object, on the climber over here, which is going to be 8358 plus 940.3. This gets multiplied with 2, and this entire thing will be divided over. Extension was 1.35, right? And now you're going to get 13,775 Newton, which is obviously approximately closer to 10,000 kilonewton, 10 kilonewton, right? And again, if you guys have trouble in remembering this formula, this is the formula that we get from your force extension graph, right? The force extension graph This is force, this is extension. The gradient would have given you stiffness, sorry, spring constant. Force over extension is equals to spring constant, and the area of the graph is always a triangle, because we will always calculate the area for the linear section of the graph, which will always create the shape of a triangle. This will give you the elastic stored energy. Okay, so using this, you are going to calculate that how much maximum force was applied onto the climber while it was falling a certain distance of 12 meter and that extension of 1.35 meter. Okay, so we'll move on to the next question. It says that a new climber suggests that a longer length of rope would between the loop and the climber, as this would absorb more energy from a fall. We need to comment on this extension. Okay. Now it was already given at the start that whatever the energy that was exerted from the fall was received by the rope, right? Now it says that if we are going to use a longer length, then most of the energy from the fall will be received by the rope. In that case, there will be less chances of having an injury for the climber. Now we need to comment on this statement over here. Okay, it says that a new climber suggests using a longer length of rope between the loop and the climber, as this would absorb more energy from a fall. Okay, let's just understand that why the new climber thinks like this. Because absorbing energy is obviously related to your what? Half force and then extension, right? So obviously if you're going to use a longer length, that means extension will be larger. So that may, in that case, energy absorbed by the rope will be larger. But then again, if your extension increases, right, your energy absorbing amount increases, and because of that, force would also increase. And in that case, if force increases, your climber is going to decelerate at a higher rate this time, and obviously this would create a larger force experienced by the climber. And if a larger force is experienced on the climber, then the climber will certainly receive a higher chances of injury. Right, another thing to explain over here, let me just do this 1 minute. Okay. One part over here is again, this is not a good idea. That why this is not a good idea, let me explain that. This is not a good idea because as the climber would reach a higher velocity, right, before the rope would begin to stretch. Like for example, if you on your diagram over here, the entire distance fallen was divided into two sections. 12 meter for the distance fallen, and then again an extra of 1.35 meter due to the extension. But if you're going to use a longer length, then extension will be larger. If extension is larger, that means after traveling a 12-meter distance, it will again travel a further 2-meter distance. For a longer distance, what? Velocity will be higher, right? Because if you remember, V is equals to D by T. If your D increases, V would also increase. And for a higher velocity, F equals to M change in V over T. I'm not using exact acceleration. If your velocity increases, force will also increase. That means a larger force will now be exerted onto the climber. As the rope is going to stretch for a greater extension, a longer force or a larger force is going to be exerted on the climber. And because of this larger force, the climber will now receive a greater amount of force. And obviously because of a greater amount of force, the climber would receive a larger injury, right? That is not a great idea over here to use a longer length. So we are going to start with that. This is not a good idea as the climber would reach a higher velocity, as a climber would reach due to longer length, I'll just write due to larger extension because of longer length of rope. length of rope, and then again for larger velocity there will be a larger force as the rope stretches, so creating them more, like increasing the chances of injury for the climber. As the rope stretches, on the climber. Okay, this is how the entire working would be. Then we'll move on. It says that a climbing rope manufacturers recommend that ropes are replaced every 5 years. The force extension graphs up to the breaking point for 1 meter length of a rope when new and after 5 years are shown. Okay, this is a new rope and this is a rope after 5 years of being used. It says that comment on the manufacturer's recommendation, and you need to use in like include calculations over here. The recommendation was that the ropes are replaced every 5 years. Okay, it says that after every 5 years ropes will be replaced. Okay, now this is a force against extension graph, right? Over here we cannot certainly calculate the actual area. I mean, we can calculate the area by using the approximation method. So let's do that, because as we need to calculate, like include in calculation, so we have to do that. So we have to use the approximation method to calculate the area. Now I am going to assume that this portion is equal to this portion, but then again this is not entirely equal. Yeah, I mean, I'm going to assume that this portion over here is equal to this portion, and then calculate the area under this rectangle over here easily. As I'm using approximation method, this is one of the approximation method. Other than that, for the blue graph again, I'll have to calculate similar thing. So for the blue graph, now I am going to assume that this portion, which was not actually originally in part of the graph, is equal to this portion. So I'm going to reject this portion and take this portion into my calculation. So in that case, for the area under the graph for this new row is going to be this entire section, which is now what? This is 500, 600, 700, 800, 900. Yeah, this is like 600 over here. Let me increase the. This is 600 over here, and this is approximately 0.10. This is 0.15, right? 0.15 divided by 0.1 divided by 10 units in between them. So every unit is 0.15 minus 0.1 divided by 10. So you get 5 into 10 to the power of negative 3, and there you have 1, 2, 3, 4, 5, 6, 6.5. Okay. So 5 into 10 to the power of negative 3 multiplied with 6.5. This is 0.02325 plus 0.1 is 0.1325. Over here, this length is actually 0.1325. And how did I calculate that? I found out the difference in between the two units, which was 0.15 minus 0.1 divided by 10, because these two units were separated by small 10 units, and then I multiplied it with, like, this was the value that you're going to get for every small line over here. This one is actually going to give you 5 into 10 to the power of negative 3. So there are 1, 2, 3, 4, 5, 6, almost 6.5 small lines, where every line would give you this one value, 5 into 10 to the power of minus 3. So that's I'm going to multiply 6.5 with this. And again, this difference has to be added with this 0.1, right? So that means from all this value, we're going to add 0.10, and then we're going to get 0.1325. So over here, the energy and like area under the graph is going to give you the energy stored, right? So we can find out the energy stored for the new graph, for the new wire, is actually going to be what? 600 multiplied with 0.1325. Yeah, 600, 0.1325. That is almost 79.5. So that's 600, that is 6,000, because over here you're getting um, thousands on the y-axis, right? Sorry, so 6,000 with 0.1325, you're getting 795 joules. Okay, and then similar working has to be done for your this portion, for that older wire. We can clearly understand the older wire is going to receive a smaller area, right? So in this case, now you have 1, 2, 3, 4, 5, 6, 7. So this is going to be what? 5 into 10 to the power of minus 3 multiplied with 7 and then added with 0.15, right? So this is 5 into 10 to the power of minus 3 added with 7 and and lastly added with 0.15. So I subtracted that. Now wait, 5 into 10 to the power of minus 3 multiplied with 7 added with 0.15. So you're going to get 0.185, 0.185, and the y-axis over here is going to be, this is 400 and 500. This is 3,500, right? 3,000 and 3,500. So this multiplied with 3,500 gives you 6,470. 47.5. So energy for the older wire is approximately 647.5 joules, which we can clearly understand that new wire has a greater energy than the older wire. And what else we can measure over here? Other than that, we can also measure the stiffness over here, but for the stiffness, we need to use a tangent over here because this is not a curving line, right? With the stiffness, you have to draw a tangent this time. So for example, I am going to draw a tangent over here. I think I should have used a smaller, thinner line. Hmm. This one is better, but I'm going to change. Yeah, this one is better. And then again, I'm going to draw a different line for the second graph. Hmm. I'll just erase these portions. Right? I'll just erase these portions because these are not needed anymore. Now I will draw the okay. Now again from this part I can find out the gradient, which is going to be over here. 1 minute. The y coordinate over here is approximately 13,500. Yeah, this is 13,500, and the y-axis over here is 5 into 10 to the power of minus 3 multiplied with 4 and then added with 0.1, which is 0.12 exactly over here. So for this point, right, for this specific point, the coordinates that you are getting is 13,500 and 0.12. Okay, and then again for this point, you are getting 5,500, and the x-axis over here is 5 into 10 to the power of minus 3 multiplied with 6 and then added with 0.05, which is 0.08 over here. So for that point, you are again getting 0.08, yeah, 0.08 and 5,500. So if you want to find out the change in y-axis over here, that is going to be 13,500 minus 5,500. Right. So for that new graph, change in y-axis is going to be 13,000, or we can find out the gradient easily from directly, which is going to be gradient, and that is going to be 13,500 minus 5,500 divided by 0.12 minus 0.08. Okay, and then again we have to do the same calculation for this black graph also, for this old graph also. For that old graph, the change in height was on approximately over here, that is 9,500, and this was exactly 3,000. Okay, and on the y-axis you have 0.2 minus 5 into 10 to the power of minus 3. I mean, that's just only 1 unit away before from that, which is 0.195 over here. This is 0.195, this point, and this point is 0.11. Let us clear into that. So in that case, for the new graph over here, new graph gradient, old graph gradient is going to be 9,500 minus 3,000 divided by, this one was 0.195 and this one was 0.11. 0.11. Okay, and this calculation will give you the gradient for this graph. Okay, now we have the energies, we have the gradient. I will just write down the energy and gradient and front at top, and then calculate the write down the statements over here. So this is for new row, and this is for old row. Okay, so for new row, energy absorbed was calculated using, I'm just going to use the data. Wait, 33,500 with 0.185. So it was actually 6,000 multiplied with 0.1, 6,000, 0.1325, which was 795 joules. And then again, energy over here is going to be 3,500 multiplied with 0. What over here? 0.1325. It was 0.185, but for this case it was 0.185, and you got 647.5 joules. After this, we calculated the gradient, which is the stiffness. I'll just write this as stiffness over here. Stiffness is going to be not exactly stiffness. Force against ground extension will give you stiff constant, right? Spring constant, not stiff constant. Sorry, spring constant that you got as For the new rope, it was 13,500, 5,500, 0.1, 0.08. So 13,500, 5,500, and then again for spring constant, for the older rope was 9,500, 3,000, and 0.195 and 0.11. This one, okay. So wait 1 minute. This is 9,500, 3,000, 0.195, and then 0.11. Okay, and then you're going to get that value for spring constant for older and newer wire, which is going to be 200,000, and then 9,500 minus 3,000 divided by 0.195 minus 0.11, that is 76470. Right, this is the value. And obviously this is a Newton meter. And now we're going to write down the explanations that area under the graph determined the stored energy. So for the new rope, energy absorbed was greater than the older rope, and then again that means that less energy was absorbed by the older rope, right? And then again, using the equation of K is equals to force over extension, we can calculate. The student can calculate the spring constant for both the ropes at the same apply for both the ropes, and then again we can say that the older rope is not as stiff as the new rope, so it would extend more, right? So for a smaller rope, for a smaller force, the older rope will extend more and it will also break at a smaller applied force. So therefore, less stress, less maximum stress experienced by the older rope, or can be withstand by the older rope. So we can now write over here the statement that new rope was how much times bigger? That was 695 minus 795 minus 647.4. That is almost 1.47.5 joules more. Right, then energy stored by the new rope was 147.5 joules more, and then again the gradient would give stiffness, so spring constant, which is again larger for this new rope. So therefore, the older rope is not as stiff as the new ropes. It will extend more for a smaller applied force. Therefore, the older rope is not as stiff as new rope. Therefore, the older rope is not as stiff as the new rope, and it will extend for a smaller force. It will extend for a smaller force and therefore also break at a smaller applied stress. Applied stress. Okay. Yeah, this was the working for question 17. I hope question 17 was clear. The graph calculations were a little tricky because usually this much time they do not actually ask for this kind of questions, right? But then again, they are obviously going to give you marks for these 4 points, right? Calculating the gradient and area in the graph will give you 4 marks, and for the statement, they again giving you 2 marks. Okay, so this was it. We'll move on to question 18. This is the last question of this paper. When the water vapors in the atmosphere, atmosphere cools, it condenses, forming a tiny drops of water. These drop increase in size by colliding with each other and fall back to the ground as rain. The the raindrop falls in through air. It eventually reaches its terminal velocity. The upthrust on the raindrop can be considered as negligible. Explain what is meant by the terminal velocity of the raindrop, and your answer should include a free body force diagram on the raindrop with terminal velocity has been reached. Okay. Terminal velocity means that it is a maximum, not maximum, it is a constant velocity reached by the rain whenever the acceleration is entirely zero. And on the diagram again, we have to draw forces, that is weight, drag, and upthrust are on this case, right? Where all the forces are in equilibrium, resultant force is zero, and this is how the terminal velocity is explained. I'll consider this as a repeated question again because this is like an entirely theoretical part, right? It never changes in any of the situations. So over here, as it was falling, that means upthrust and drag will be in the upward direction, weight will be in the downward direction. So you have weight, this is drag, this is upthrust, and this is weight. So we can write that at terminal velocity of object, over here we should refer this as raindrop, as it is in so equilibrium where all the forces are balanced. Where all the forces are balanced to each other. In that case, we can write drag plus upthrust is equals to weight. I think it would be better if we could write this in terms of words. That is weight is equals to drag plus upthrust. Right, like this. Okay. That was it for part A1. We'll move on to the next part. It says that the air resistance F acting on the air raindrop falling at a velocity of v can be determined by the expression this, where A is the cross-sectional area of the raindrop, P is the density of the air. We need to calculate the terminal velocity of the spherical raindrop. Over here, spherical raindrop indicates that Stokes' law is applying over here, right? Of radius this, density of air and density of rainfall is given. Okay, we want to find out the value for calculate the terminal velocity, right? Okay. Density for air surface A gives you the cross-sectional area, and V over here was the density was the terminal velocity. Okay. But we do not have the value for force, right? Okay. Force is going to be the mass over here, right? The weight of the rainfall itself. But we also do not have the weight over here. We can find the weight of the rainfall, rainwater using the density of the rainwater, right? So at first, let's just find out the force, which is weight. So force is actually weight, which is basically mass into gravitational field strength, but then again mass will be broken down into density over volume. So density into volume, right? So density into volume, so capital V and then G. So density over here, density of the rainfall was 1 into 10 to the power of 10 to the power of 3. So 1 10 to the power of 3 multiplied with volume is going to be 4 by third pi r cube because this was a sphere. So 4 by third pi r is 2 into 10 to the power of minus 3. Entire thing will be under a cube. So yeah, right. 2 into 10 to the power of minus 3, entire thing under a cube, and this will be again multiplied with 9.81. So this is 4 by 3, 4 pi multiplied with 2 into 10 to the power of minus 3, again multiplied with cube, and you get multiplied with 9.81. Yes, the total weight is 3.29 into 10 to the power of minus 4. So this is 3.29 into 10 to the power of minus 4 Newton. And other than that, nothing else is needed. Only the area for this um, raindrop will be needed because it is provided over here, required over here. But we can obviously calculate that within the equation. So equation was F 0.45 density of air. This is the density of air, right? Was stated over here. Density of air, area of sphere multiplied with V square. So if you just make V the subject, this is going to be force multiplied with, sorry, not multiplied with, force divided by the entire thing, 0.45 density of air, area, entire thing under a root, which is force over here was 3.29 into 10 to the power of minus 4. This will be divided by 0.45. Density of air is going to be 1.2. Area is going to be pi r square. So pi 2 into 10 to the power of minus 3, entire thing under a square, and everything under a root. So I'm just going to calculate this exactly like it is in the screen. 3.42 into minus 3 divided by 0.45 into 1.2 into pi into 2 into 10 to the power of minus 3, entire thing under a square. And if I calculate this gives you math 0. 1 minute. Maybe I made a mistake. Into 10 to the power of minus 4, 0.45, 1.2 into pi into 2 into 10 to the power of minus 3 pi r square, right? It's 6.96299, like approximately we can write 6.97 over here. Terminal velocity is 6.97 meter per second, right? So this is how you're going to calculate the terminal velocity. After this, we have part B to finish. So for part B, it says that some plants have adapted to high rainfall by having a specialized shape and waxy leaf. This allows rain to slide down a leaf and off the end as a series of drops. The drop of water slides off a leaf as shown. Add to the diagram to show the position of the raindrop at regular intervals of time. First two positions have been drawn for you. Okay. Oh, this is going to be the overall shape, right? This is how the entire rainfall will fall. So I'll just write down drops over here, right? And I think other than that, no other explanations what was needed. Um, yeah, this is how the entire working will be. Like this is like a term, like projectile motion over here, right? Vertical displacement increasing where the horizontal displacement remains constant because in the projectile motion, object only accelerates vertically and horizontally it moves with constant velocity. Okay. Now it says that water falls from a leaf at a steady rate of 5 drops per second. Okay, this is your velocity now, 5 drops per second. Each drop reaches the ground. There are 4 other drops above above it. Okay, like every time each drop will reach the ground, there will be 4 other drops above it in air. When you calculate the height of the leaf from the ground, it can be assumed that the drop at the highest position has left the leaf. Okay, now it was already stated that 5 drops per second, right? So what I will do over here is that I will, actually draw that line and not draw this much of drops over here. Okay, I'll just specifically draw 5 drops. Already 2 is drawn for me, so I'm going to draw 1, 2, and then the last one will be exactly on the ground. Okay, this is the 5 drops. Now from this part again, it was stated that the speed was 5 drops per second, right? 5 drops per second means that time would be 1 over 5, that is 0.2 seconds. That means at every second, like we are doing unitary method over here, if for 5 drops it takes you 1 second, that means for 1 drop it's going to take 1 over 5, that's 0.2 seconds, right? That's what we did over here. 1 over 5, 0.2 seconds. Okay, now after this, now we know for every drop it will take 0.2 seconds. How much time, like this is already on the ground, right? So between this session you have 0.2 seconds. This part you have again another 0.2 seconds. From this position you have another 0.2 seconds, and from this part you have another 0.2 seconds. That is like 0.8 second, right? Because you have 4 0.2 seconds, so that is 0.8 seconds. That means total time over here for all these 4 drops to reach the ground will be 0.8 seconds. So now you can use the equation S equals to ut plus half at square, where this entire thing will be 0 because every over here the drops were dropping from that leaf, right? So initial velocity was 0. So S will be just half 9.81 multiplied with 0.8 square. How did you got that 0.8? Because for one leaf it was taking 0.2 seconds. For 4 drops it is going to get 0.2 into 4. So that's why you get 0.8, right? So this is the overall calculation. 0.8 seconds. So which is at this point 3.14 seconds. Yeah, this is it for this entire working. 3.14 meter over here. The total distance, the height above the ground for that leaf.